Welcome to this explainer. Today, we're bridging the gap between microscopic physics and computational logic. We're going to trace the fascinating journey from the behavior of individual atoms all the way up to the complex computer brains that power our modern world. Here is our roadmap for today. We'll start with the p-n junction basics, then move on to let there be light, followed by an introduction to logic gates, and finally wrap up with advanced logic and math. Let's get right into it.
All right, let's dive into section 1, the p-n junction basics, the microscopic foundation of it all.
So what exactly is a p-n junction? Well, it relies on a super delicate balance. By intentionally introducing impurities, a process we call doping, we actually create a dynamic equilibrium where the diffusion of majority carriers perfectly balances the drift of minority carriers. Now, this doping process gives us two totally distinct materials. Doping silicon with something like boron creates a p-type semiconductor, which leaves these extra holes that act as positive charges. On the flip side, doping with phosphorus gives us an n-type semiconductor, and that one is absolutely packed with highly mobile, negatively charged electrons. When we actually join these two types together, it creates a depletion layer of immobile ion cores. Think of it as a microscopic wall, a potential barrier we call V0, that effectively prevents those carriers from just freely mixing across the boundary. But here's where it gets incredibly cool. The real power comes from actively controlling that wall. Applying a forward bias voltage actually shrinks the depletion layer, letting current flow freely. Flipping it to a reverse bias drops the voltage across the depletion region, which raises the wall and totally blocks the current. It's basically a microscopic traffic cop. So let's say we apply that forward bias, lower the wall, and let the current flow freely. The minority and majority carriers cross over and recombine. But that brings up a really critical question. What exactly happens to the energy that gets released during that recombination? Well, that brings us to section 2, let there be light, all about a phenomenon called electroluminescence. You know, in a standard silicon diode, all that recombination energy is just lost as heat. But if we engineer heavily doped p-n junctions with very specific materials, that energy is released as actual photons. This is that optical and electrical phenomenon known as electroluminescence. So, believe it or not, LEDs are really just highly specialized forward-biased diodes. By tweaking the chemical alloy, like using aluminum for reds or indium for blues and greens, we can completely dictate the exact wavelength and color of the emitted light. And because they're solid-state junctions, LEDs absolutely leapfrogged older incandescent tech. They run on super low voltage, output pure monochromatic light, and activate instantly with zero warm-up time. That makes them the absolute standard for everything from the smartphone display in your pocket to those massive advertising billboards. All right, so we've successfully controlled our p-n junction to act like a one-way street, and we've even manipulated it to emit beautiful colored light. But that brings us to a huge, fascinating question. How on earth do we go from a simple blinking light to the complex, mathematical, computational brains of computers? Let's figure that out in section 3, Introduction to Logic Gates, where we transition from light into logic. To actually make a computer think, we use logic gates. By mapping physical voltages to a binary logic system, where 0 volts represents a 0 and 5 volts represents a 1, we basically trick these physical hardware components into evaluating logical rules for us. Take the standard OR gate, for example. You can kind of think of it as the inclusive, easygoing decision maker of a circuit. It takes two inputs, A and B, and evaluates them into a single output, Y. The logic here is super simple. The output flips to a high state, a 1, if input A or input B or both are active. It only returns a 0 if the entire circuit is dead. On the flip side, we have the AND gate. This one is much stricter. It acts as a true coincidence circuit, meaning it demands absolute alignment from its inputs. Even if just one input is high, the AND gate totally rejects it. It only passes a 1 if, and literally only if, both inputs are perfectly aligned at 1 at the exact same time. Which leads us to our final part, section 4, Advanced Logic and Math, and the Boolean frameworks that make it all work. To do really complex math, we need one more fundamental tool in our toolbox, the NOT gate, also known as the inverter. It takes a single input and just flips it completely upside down. If the input is low, the output is high. If the input is a 1, it outputs a 0. It's basically the ultimate contrarian of our digital ecosystem. Now, the real magic happens when we start combining these things together. If you attach an inverter to an OR gate, you create a NOR gate. If you append one to an AND gate, you get an AND gate. These composite gates actually form the absolute bedrock of all modern processing architecture. Because the inverter totally flips that strict AND logic we just talked about, a NAND gate outputs a high, 1, in almost every single scenario, only dropping to 0 when both inputs are 1. This predictability is so incredibly powerful that NAND gates are considered universal. You could theoretically build an entire computer using nothing else. And because all these hardware gates are flawlessly predictable, they map perfectly onto Boolean algebra. By using frameworks like De Morgan's theorems, engineers don't even have to guess. They can mathematically prove and design billions of microscopic gates on paper before ever etching a single silicon wafer. So we've traveled from doping raw silicon to manipulating microscopic barriers, all the way to processing binary math. It leaves us with a pretty profound thought. The incredibly complex digital ecosystem you're using to experience this explainer right now is, at its core, just millions of microscopic p-n junctions, tirelessly routing traffic at the speed of light. As we continue to push the boundaries of things like quantum computing, one has to wonder, what fundamental physical barrier will we manipulate next?